Hello. In this video, we're looking at this as 1.6 part 3, but basically what we're doing is we're taking a big picture review of the limits. So we'll start off with a lot of the equations and go through a lot of the techniques we developed in the beginning of 1.6. Technically, these are all using the limit laws, but we've kind of seen just the basic idea. Trying to plug in. If it plugs in and things work out well, you're done. If it doesn't, the different cases, k over 0 goes off to the infinities, 0 over 0 requires manipulation, whether that manipulation is factoring, conjugate, cleaning up fractions, but any way you manipulate, you should be able to simplify and then try to retake the limit. We saw piecewise functions, just have to be very careful about which piece of the equation to use. And then at the end, we'll still do a little bit more with the graphing that we saw in 1.5. So limits are a major topic, everybody. This is such a building block. As we move on in section 1.8, we'll talk about continuity, but we're gonna need limits. And then in section 2.1, we're gonna introduce the derivative, but it still starts with limits. So your first test, your first quiz is entirely limits. This little review pack right here, these problems are an excellent review for your first quiz. And then when we get to our first test, there will be some basic limit questions, but all the other topics involved all still have limits somewhere in them. So you really want to make sure you take plenty of time to do this well and get these basic ideas in order to move on in a good way in this class. So what I'm going to do first, I have several problems here. I want to show all of them to you. So if you want, you can either just go through as I go through in just a moment, or if you want, you can pause, go through, do these, either do them all at once or try and take a look at them, go through them one at a time, and then come back and check yourself. So either option, either way will be very good. There's one more page, a few more problems. This last one uses the graph. So you've got your graph here, and then all the different questions. Okay, so I'm going to jump in and start solving. I'm not trying to go fast here. I'm just trying to work in an efficient way, trying to point out our thought process, how we should be thinking, how we should proceed. So problem number 1, a limit given an equation, we start by plugging in. I plug in the 7, 7 plus 2 is 9, so I have the square root of 9 minus 3 over 7 minus 7, and that's 0 over 0. And that is one of our big cases that tells us basically nothing, okay? And again, it's important to do this, everybody. You can sometimes just get caught up doing extra work, sometimes get caught up doing things that are completely unnecessary, and how many little mistakes that could come from that. So make sure we're on the right track. We plugged in. Once I plugged in, I dropped my limit notation, but this tells me nothing. So I need to go back to the beginning and I need to manipulate. How will I manipulate this one? I will manipulate using the conjugate. There's the radical component, the conjugate. Even in this one, now we're seeing the radical has a little more to it. In our previous ones, we've just had rad x. Now we've got radical x plus 2, but still, first piece, second piece, those pieces stay the same. It's just the sign between them that changes. And it's this sign that changes, not the sign under the radical. That's a part of that first piece. And whatever I do to the top, I also have to do to the bottom. While I am technically multiplying both the top and bottom, I'm actually only going to multiply out the conjugate pair, which in this case happens to be in the numerator. And when I do that, radical x plus 2 times radical x plus 2 is x plus 2. The middle terms will cancel. You get a positive 3 radical x plus 2 and a negative 3 radical x plus 2, like terms that cancel, and then the last two multiply to be minus 9. But again, through experience, if you haven't done any of this before, if you haven't seen any of the videos or worked through any problems, you wouldn't know. It's easy to now just start foiling this out as well. But from experience, we know we're going to want things to cancel. So we're going to leave these two pieces. They're still attached by multiplication, but we're gonna leave those two pieces still separated so that they're still factored. And now, and maybe you already cleaned up the top a little bit, that the plus 2 minus 9 becomes a minus 7. X minus 7, 7 minus x. I mean, we've seen a couple of times these are just perfect, exactly match and cancel. These are not perfect, but they're close enough. So I'm going to factor a negative 1 out of the top, and then it will literally become minus x plus 7. But I'm just going to change the order so that now it does match. Now these can cancel. So the conjugate part, there was the manipulation. The little bit of cleanup led to this simplification. Good habits, everybody. Still keeping my limit notation. I drop the limit notation when I go to plug in, and right now I'm still cleaning up. All that's left in the numerator is a negative 1. The denominator, the radical x plus 2 plus 3. I've done a lot of cleanup. Now I'm going to try and take the limit again. This is where I drop the notation, and as I plug in the 7, I get a good answer. The negative 1 is still there. Radical 9 plus 3 becomes 3 plus 3, so negative 1 over 6 for our first answer. Moving right into number 2. Still, start off by plugging in negative 3. And when I do that, I get 1 divided by 0. This is the k over 0 case. 0 in the denominator. Either one of these, there's something a little extra here. There's some extra consideration that needs to be made. But 0 over 0, you have absolutely no idea what this answer is going to be. It could go anywhere. It could be infinity. It could be 2. It could be negative 10. Anything can happen, so we need to manipulate to get to a cleaner version to get that answer. But k over 0 is going to an infinity. But which infinity? Well, I'm going to have to approach from both sides here. I had just approaching negative 3 in the original problem, so I'm going to have to consider both sides. And I just am checking the signs. I don't care numerically the values. I know it's an infinity. It's just the signs to figure out whether it's positive or negative infinity. So negative 3 from the left, that would be like negative 3.1 coming from this side on the negative axis, on the negative side of the x-axis. So negative 3.1, 4 minus 3.1 is positive, but negative 3.1 plus 3 is a negative. So from the left, a positive over negative gives me a negative, so we're going to negative infinity. But now as I approach negative 3 from the right, now, again, a negative value from the right, so I'd have something like negative 2.9 here. I'd still get a positive up here. 4 plus a negative 2.9 would still be a positive. And the denominator. By the way, everybody, that's really it. Right here, we had a positive 1. I knew these were going to be positives. It's the denominator. It's the 0. How are we getting to 0 from the positive or negative side? That's what we really didn't know. But I still think it's a good habit to check both top and bottom, make sure we're staying on track. We shouldn't get different parts here, but we may get different parts here. And we do, because in this one, if I have negative 2.9 plus 3, that would also be a positive. So from the right, we are going to positive infinity. These are not the same infinity. I mean, that's why we had to do all this work. Otherwise, we would have just left this as our answer. And the fact that we're not getting the same infinity, the final answer to number 2 is does not exist. From the left, we're shooting down forever. From the right, we're shooting up forever, but we're not going to the same spot. And just the little things we mentioned here, you know, some people, they like to jot down a little more. What is the actual x they're using? If you go too far, we've always mentioned when we're thinking about approaching from both sides, whether it's a situation like this or if it's in a piecewise function, if you go too far, and if you say something like negative 5 and negative 4 are approaching negative 3 from the left, I mean, it's true they are on the left, but they're not approaching. They're too far away. And if you use those values, well, you'd have 4 plus negative 5, and all of a sudden you'd be getting a negative here. Or even if you use negative 4, 4 minus 4, now you're getting 0, and now you're not getting a sign. So remember, when you're doing this, the value you pick may be an ugly decimal, but you don't have to go crazy with the arithmetic just to keep track of the signs. Moving into number 3, now we've got that h problem, but I still should think in that same way. If h goes to 0 and I'm just plugging 0 in for h, x may go away, but it may not. X certainly can be a part of our answer here. Can't be a part of our answer here. If the limit as x approaches a value, if the limit is over x, x is going to be gone when we're done. But here, since the limit is over h, x can still be there at the end. But now, if I let h go to 0, I get x squared, x plus 0 squared, which is x squared, plus 7x, and I've still got minus the quantity x squared plus 7x, and there's an h all over 0. And careful here, if you look too quickly, you might think you're in a k over 0 spot, but look a little further here, either distribute the negative or realize this minus quantity the exact same thing. These are canceling. This is 0 over 0. So it's more like number 1 in that this is another case we just have to manipulate. Well, how do we manipulate this one? It's so many of these problems, the 0 over 0, it's what can you do? Problem number 1, there was no good factoring. There was nothing really else you could do. The conjugate was your only choice. Problem number 3, what can you do? Well, you got all these parentheses. Let's get rid of these parentheses. But now I'm back to manipulating. So while I manipulate, good habits, keep the notation, still keep the limit. Again, I dropped the limit here because I tried plugging in h was 0. But now that I'm back to playing with the equation and h is still there, I need to keep my limit notation. So FOIL this out. Again, no shame, do this off on the side, x plus h times x plus h. As you FOIL, x squared plus xh plus hx, just realize you can combine those, plus h squared, just showing you off on the side. You'll get x squared plus 2xh plus h squared. Here, distribute the 7 plus 7x plus 7h. Here, distribute the negative sign, minus x squared minus 7x. And now we just started, but now notice what happens from here. Now that we've expanded this, now things start to clean up nicely, right? Positive x squared, negative x squared cancel. Positive 7x minus 7x cancel. Here's another good spot, everybody. Know yourself. Some people are perfectly happy to keep working right here. Others, this is starting to get a little messy. They'd rather rewrite. Let me squeeze it in right here. The limit h approaches 0. I have 2xh plus h squared plus 7h all over h. It's tempting to think we've already done simplifying, so try to plug in h as 0 again, but you'd still get 0 over 0, just showing us we haven't manipulated enough, or we haven't simplified enough, right? You plug in 0 for h again, 2x times 0 is 0, plus 0 squared is 0, plus 7 times 0 is 0, all over 0. But now that we got those extra terms out of the way, and as we mentioned when we saw this in section 1.6, we got to expect that we're going to need to cancel this h. And now by getting rid of these other terms, the way they worked out, now we can do that. You can either think of this as factoring the h out of the top, and that's what's left over, and that allows you to cancel off the common h. Or other people just look at it as just dividing, but make sure you divide all three. You can't pick and choose and say, I just divide this one by h and these stay the same. You'd have to divide them all. And now we're just about ready to wrap this one up. We have 2x plus h plus 7, but now we have really cleaned up a lot. And now when I let h go to 0, I am left with 2x plus 7. And again, compared to some of the other limit problems, that feels weird because we have a variable and a number. But as we said at the beginning of this, there are no h's, and that's what was the most important part. Okay, and now we'll come down to number 4. And I still start by plugging in back to an x problem, not quite as goofy as having the h, But again, everybody, you can't just look at this as goofy. This is not going away. This is actually giving us a sneak preview into chapter 2, the beginning of chapter 2. So as we said in the video, we don't know what h is doing yet, but we will. So you don't want to ignore this. You do want to get some practice with these. But again, back to some of the more common ones. Now x is going to -4. So again, I plug it in. -4, order of operations, everybody, be careful here. -4 squared is 16, times 3 is 48. 12 times -4 is -48. So there's a 0. And in the bottom, 16 minus 12 minus 4. Again, important to plug in, but don't rush through this. It's easy to make little goofs, and all of a sudden, like we said at the top, you get k over 0 when it should be 0 over 0, or vice versa, or you don't get a 0 in the bottom. So be careful with your arithmetic, but we are back to a 0 over 0, so back to the beginning. And now what do we think about this one? Well, this one factors. How can we manipulate? Well, both of these are nice polynomials, so we'll factor. The top, I'll take out a GCF of 3x, and I'll be left with an x plus 4. The bottom, a nice trinomial into two binomials, x and x. How do you multiply and get a negative? Well, one number is positive, one is negative. And now with opposite signs, I need these to add, which with opposite signs is really subtract the +3. So what multiplies to -4 and adds to +3? +4 and -1. Here's another little hint, everybody. If factoring is your key to manipulating, if that's what you can do, you've got to see a common factor cancel. So if you accidentally goof this and had a -4 and a +1, and now nothing cancels, that should really be a sign something is wrong. Now, maybe what's wrong is that we didn't need to factor, that it wasn't a 0 over 0, but in this case it was a 0 over 0, so that would point out that, no, I must have made a factoring mistake. Now you could fix it. Now you see your common factors cancel. I'm going to make a small mistake here, everybody. I'm going to write that. And then I'm going to write equals, and I'm going to get -12 over -5. And you may be saying, well, what's wrong with that? That's what I would have done. But here's the issue, everybody, the notation. This does not equal -12 over -5. The limit of this expression equals -12 over -5. Without that limit part, this becomes nonsense. Now, I'm not going to hammer you on that on a quiz, but that is something that is like a -1. So we don't want to lose silly little points like that, especially when we know what we're doing. So you want to make sure you're embracing the notation, not fighting it. And by the way, at the end here, -12 over -5, that's fine, but certainly a negative over negative is a positive. The fraction doesn't clean up, so that's certainly fine. But if you wanted to play with that, that's 2.4, 2 2/5, but there's nothing wrong at all with fractions, even if they're improper. That is a perfectly good answer. Okay, moving right along. Now I'm up here looking at number 5. I plug in 3, 1/3 minus 1/3 over 3 minus 3. Another 0 over 0. Again, lots of experience with 0 over 0. So another 0 over 0. Now we need to deal with the fractions. So again, this type of problem, some people kind of do this all at once. I like 2 steps. Make the top one fraction, common denominator. X and 3 are the individual denominators, so 3x would be the common denominator. This one's missing the 3, so I can't just multiply the bottom. I have to do the same on top. This one's missing the x, so top and bottom by x. Now I've got a common denominator of 3x, and when I actually clean up the top, 3 times 1 minus 1 times x, I get 3 minus x over 3x, and not to forget the 3 minus x that was just hanging on for right now. The point of doing this, make the top one fraction, the bottom put it over 1, so we can treat that as a separate second fraction. A divided by b, we multiply by the reciprocal when we are dividing fractions. So dividing by 3 minus x over 1 becomes times 1 over 3 minus x. Sometimes, this is quite lucky, We saw some in the practice exercises that we were doing that we might have to do a little bit more work before we see cancellation, but this one cancels very nicely. So I'm left with 1 on the top, 3x on the bottom. A lot of manipulating, nice simplification. Let's try and take the limit again. Plug in 3, and I get 1/9. Again, you notice we've gotten several fractional answers in this so far. Definitely possible. That's why, notice, I have not even talked about the calculator. It's not easy to recognize if it's not a whole number. That calculator technique can be very difficult to identify what is exactly the decimal we're heading for. This is an ugly repeating decimal, repeating decimal, negative 0.1666666 forever. Not easy to figure out, even with a good XY chart. This one, 2.4 as a decimal. Again, maybe a little bit easier than the top one, but not easy. So again, calculator can help, but this should be the technique you're getting better with. You're going to need this technique. So now, number 6. Did you fall for it? Did you already start factoring these? You don't have to in this one, because our first step is not manipulate, our first step is plug in. And when you plug in x is 0 here, you get 0 minus 36 over 0 minus 0 minus 12, and that equals positive 3. You're done. So that's what I was saying at the beginning. We still, even though we are getting so used to dealing with the k over 0, the 0 over 0, by far most of the homework and the review problems we've seen have done that, but we still want to maintain good habits. We still plug in first. And now it wouldn't have been terrible, but if you started factoring, this is x minus 6, x plus 6, this is x minus 4, x plus 3. But then like I was saying on the previous page, now nothing cancels. And you think you factored wrong and you start making things up and just getting into a big mess. So we're not just trying to memorize steps, we're trying to get a big technique. There are steps we can follow, but we want to make sure we're following them to get ourselves in the best final answer, not just spinning our wheels and wasting time. Okay, now for numbers 7, 8, and 9, we're going to use this piecewise function. So a lot of figuring out the piece. As x approaches 1, which piece shall we use? Well, approaches 1, we got to think of 1 from the left, 1 from the right. We cannot just say, this is the one where the place where the 1 is equal, where the 1 is included, so use this. That would be f of 1, not the limit. The limit, we got to think about things like 0.8, 0.9 from the left, 1.2, 1.1 from the right, and the 0.8, 0.9 from the left, we're up here, we're going to need this definition, and the 1.2, 1.1 from the right will be in this section, so we'll use this definition. So we're going to need to break this one up. We're going to need to take the limit as x approaches 1 from the left and separately 1 from the right. I'm writing it out a little more formally here. We've done this a little shorter like I did with the k over 0. Some people just show this and the appropriate piece. You do want to get in good habits, not only with the techniques, but just showing me a little of your work. You don't have to show me a ton, but just to show me a little bit so you're not just pulling answers from thin air and I could follow and see you're using the appropriate ideas and techniques. So again, 1 from the left, 0.8, 0.9, 0.99. Those values are less than 1. I'll use x plus 3. 1 from the right, 1.2, 1.1, 1.01. We're in this interval, so we'll use the x squared plus 4. But now the left and the right are done. With the k over 0, I still needed those numbers because I was checking signs. But this was just to figure out which piece. Now I just use 1 for both of these. I plug 1 in here, I get 4. I plug 1 in here, I get 5. What I got from the left doesn't match what I got from the right. This first answer does not exist. Now I move to the second one, and now I'm approaching 3. But this is a little bit nicer, because if we're approaching 3, whether it's from the left or from the right, 2.8, 2.9 from the left, 3.2, 3.1 from the right, every x value I just said is bigger than 1. So this does not need to be broken down left and right. You can, but it's just unnecessary because both the left and the right, you would just be using the x squared plus 4. So this one, really nice. Just one piece. We plug in 3, 9 plus 4, and we get a final answer of 13. Again, no problem at all writing it out. 3 from the left, 3 from the right, but you'd end up with x squared plus 4 in both of those sections, so you definitely get the same answer, and that is your final limit. We mentioned this also in the review, in the video when we were covering this. Some people with piecewise, they start to realize as long as you're not dealing with one of the turning values, it's normally a lot easier. But when you are dealing with a turning value, and now we'll see that again in problem number 9, that's where it typically takes a little bit extra work. So number 9, similar to number 7, if I'm approaching -1, well, I'm splitting. So -1 from the left, I'm up here. So I'll write this one a little more informally. Still showing what I'm approaching on which side, but I can just focus on the piece and I don't have to write the limit part. I'm okay with that. I mean, it's not terrible to write LIM, but I'm okay with that. And then similarly, -1 from the right, those would fall in here. So we'll use the x plus 3, but now I'm just plugging the -1 in both. So here, -1, 3 minus a -1 is 4, square root of 4 equals 2. And then here, -1 plus 3 is 2. This time they did match, so we do get an answer. The limit as x approaches -1 is just 2. Okay, last page, everybody. And we have 10 problems, but again, we said it before, and now that we're seeing them all together, you get even more. Every one of the equation problems took a little bit more thinking, a little bit more technique, but now that we're back, and therefore a little bit more time. Not that any one of those problems were long, but maybe, 2 to 5 minutes for each one of those, depending on exactly how fast you work, and that's a pretty good schedule. Okay, but now looking at the graphs, each one of these should be about 10 seconds, as long as we understand the differences in the notation. This time I hit us with all the limits, and then I'm going to test us on the function values before we kind of mix these up a little bit. So all the limits, considering the left and right if there's no indicator, or just the left or the right if that's indicated, but then the function values, just going directly to that x, finding the graph to get the y. So number 1, if we're approaching -2 from the left, from the right, points going here, points coming here, we're coming together. The graph actually touches. I don't care that it touches. I really care the graph is coming together right here at a y of -1. So that is the answer to the first limit. Now, as I let x approach -1, so now here's -1 from the left, from the right. So I'm looking at these points, and they're also coming together, right? Over here, these were going down, these were going up, but coming together. Here, these are going down, these are also going down, but it's just about coming together. Here they touched, here they don't, but they're still coming together. And they're coming together at this y, which is -2. So that is the answer to this limit. Next, well, now I've got the directional sign. I am only asking specifically 1 from the right. So here's 1. Without that sign, I'd be looking both from the left and the right, but just approaching from the right. So I'm just looking at these points, and these points, the closer I get to this coordinate, these points are getting closer and closer to this open circle. And this open hole is at a y of 2. But now number 4, I am just asking you to approach 1. So now both from the left and the right, well, we just looked from the right, we're up here at a y of 2. Over here, if we approach 1 from the left, we're down here, and from the left, we get a limit of -1. We're not getting the same thing, or you can look at it like we were saying over here, it's not coming together. Whether there's a huge gap between this or a little space, we're not coming together, we're not going to the same place. That's the situation where our limit does not exist. Number 5, as x approaches 2. So we're up here, from the left, from the right, and both of those, from the left, these points are shooting up, approaching this asymptote. From the right, these are also shooting up. They're both shooting up forever. They're both shooting up to a y of positive infinity. Again, if we didn't already realize this, that's a very interesting part of limits. The idea that we're approaching allows us to have an answer like this of infinity. Typically infinity, that's not a number, that's a concept. But as a limit, it is very valid to get that as an answer. It's easy to misunderstand and to think that should also be a does not exist, but they are going to the same place. They're going to the same infinity. Okay, last limit here, as x approaches 4, now I'm out here. So from the left, from the right, these points, and once again, we're coming together. Coming together at an open hole, but coming together at a y value of -1. And now the last 4, now we're just looking at the function value. So g of -1, no more left or right. We did the limit as we approach -1 up here, but now no more left or right, going directly to -1. Where on the graph, where is the graph that corresponds to x is -1? It's right here. It's the filled in point, not the open point, and that has a y of -3. Next, g of 1, again, no more left or right. Go directly to x is 1, look up and down, and there's the filled in point. The y is -1. Number 9, g of 2, go directly to x is 2. There is no point. This dashed line is indicating we've got an asymptote, and the whole point of a vertical asymptote is basically like an impenetrable wall. You can't actually touch that wall, so there is no point that's on that line. So that is an example where the function value does not exist, or undefined is also okay. I prefer does not exist. And then the same thing, sort of different reason, but similar happens with g of 4. When I go to x is 4, I look up and down, and same thing. Here there's no piece of graph, and neither is there here. Okay, back over here, we had an open circle here, filled in here, and at 1, open circle here, filled in here. So we were looking right at the x coordinate, not left or right. We were looking for the filled in. Here there is no filled in value at x is 4. So that is another does not exist.